So today I'm going to talk about word translation entropy, well, again, if there's something that's not clear or some problems in the internet or anything that you would like to point out, just feel free to interrupt me. So just a little bit of a review of what was covered last Friday. We have learned some of the regression analysis, right? And in the Python script, we see all these numbers that give us a summary of the regression results. These numbers at the first glance can be mind-boggling, but in very simple terms, what's really important in interpreting the result is has to do with three numbers mostly. So we have the R squared, which, as Michael explained, indicates how well our model explains our data, or more specifically, how much percent of the variance in the dependent variable can be explained by the independent variable. And we are also interested in the coefficient for the independent variable. So this 600 something means the change in the dependent variable if the independent variable changes by 1 unit. So here it's the it describes how much the duration is changed if insertion increases by 1. So if there is one more insertion, there would be 600 additional duration involved. So this indicates the relationship between these two variables. Other than these, we're also interested in the p-value, which indicates statistical significance. So in what I will show later on, there is some regression analysis, and I will basically focus on these three numbers. So word translation entropy. My talk today has three parts. I will start with something theoretical, the concept of entropy in general, and how entropy describes the process of translation, or mental processes of translation. I will review some of the theoretical assumptions in this regard, and then that will lead to two ways of quantifying. One has to do with shift of resource allocation, and another is reduction of entropy. I will try to argue in this part that the shift of resource allocation as represented by relative entropy is equal somehow to the surprisal of the item that's eventually chosen, and that surprisal can be approximated by in the CRITT database as the ITra. Reduction of entropy, on the other hand, can be argued to be approximated by word translation entropy, which is denoted by HTra in the CRITT database. These are conceptual and theoretical, and after that I will also show some empirical observations, starting with the prediction of effort with respect to these two metrics, namely HTra and ITra, and this will make use of the regression analysis that we have just learned last week. Then I will move on to some qualitative analysis on the eye movements, or the behavioral manifestations of the entropy reduction in the mental states. So that's the structure of the talk. Some of the major references are included here. The first one by myself is discusses HTra and ITra, entropy and surprisal, and some of the mathematics at the theoretical level, and also some regression analysis comparing the two metrics in terms of their prediction of cognitive efforts. And there are also two chapters here in 2021 in a book called Explorations in Empirical Translation Process Research. They are both part of a section in the book that specifically explains entropy and how entropy can describe the translation process. Another reference is an earlier book chapter in 2016, which relates word translation entropy to various metrics of effort, and that was interpreted as evidence of early target language activation during reading. So that also sheds light on the horizontal process in translation, which I will elaborate later on. These references can also be found on the CRITT webpage. So if you go to the CRITT at Kent webpage, there is a tab called Publications. So if we go to that webpage and scroll down, we see the workshop on empirical translation process research in 2022, and the paper that I have included is this one by myself. If you're interested, there is also a very nice video explaining the active inference theory by Carl Friston. That video also is on a YouTube channel, which includes all these talks in the workshop. Now, so this is one of the references that I'm using, and the book chapters are in this book, the Explorations in Empirical TPR. So a specific section here, you can see, is dedicated to translation and entropy. Yeah, so I'm also touching upon this chapter and that chapter by myself as well. An earlier reference was in 2016 in a book that I think Michael has mentioned earlier. If you like, I can copy this into the chat when we finish this session. So 3 parts: entropy and quantifying cognitive load, and then empirical observations. So in empirical translation process research, we have seen a lot of studies that relate textual features and behavioral data. And these studies show that various aspects of the text can predict the efficiency and cognitive effort of translation and other modes of translation production as well. For example, the number of translation alternatives for a particular source text item has been shown to have a significant impact on I-key span. I-key span is the time interval between the first fixation on a word and the start of production for its translation. This I-key span, which is basically a time interval, is strongly and significantly correlated with the number of translation alternatives. And the number of these alternatives are an aspect of ambiguity, something that is often called translation ambiguity. The same effect has also been shown in studies using decontextualized single words. And in psycholinguistics, there seems to be a general consensus that bilinguals activate both of their languages when they're working on either one. And when it comes to ambiguity, multiple meanings, and here in this case, if it's translation ambiguity, then it's the multiple translations of a particular ST word are all activated in the mind subliminally, and this is followed by a selection process in which these activated items come into competition amongst each other. This is the basis on which we can conceptualize the process or the translation choice via entropy metrics. So one metric is called word translation entropy, denoted by HTra in the CRITT database. Now, before I just describe what it means, let me just briefly show that the HTra value is in the ST table. So if we read the table, this is very similar to what we saw last Friday, but now we're reading the ST table instead of the segments. Last time we were basically looking at the sentence as a whole, and this time we're looking at individual tokens in the source text. So we read the ST table, and here is the table itself. If we go to the right-hand side, we would see a column called HTra here. Now that's the value which we use to approximate the entropy that I'm going to show. Before this column, there is another one called prob T, which is the probability of the translation of this particular translation for the ST word in question. So all these numbers are between 0 and 1 because they're probabilities. And if we convert this probability to negative logarithm, then that's what we call the surprisal or the ITra. And I will come back to that later on and describe some of the details. Just let me make sure if there's any questions. So word translation entropy, as abbreviated by HTra or approximated in the CRITT database by the HTra metric, indicates the degree of uncertainty in a translation choice, simply because of its mathematical definition. And this metric has been considered a better measure for the variation of the translation alternatives than simply counting how many alternatives there are. So in a previous slide, I've shown that the number of translation alternatives, or how many translations there are for a specific source text word, is related to various aspects of behavioral data. But here, instead of counting how many these alternatives are, it is perhaps better to use the entropy that's calculated from these translation alternatives. From a cognitive perspective, that will represent the co-activated translation options upon the encounter of the source text item. Again, empirical studies have shown a statistically significant impact of word translation entropy on various measures of efforts, including the fixation-based effort from the eye movement data, involving both early measures, namely first fixation duration and the total reading time. First fixation duration are indicative of some of the early processes in the cognitive mechanism, and total reading time would involve some of the late processes in addition to these early processes. Word production duration is simply temporal. It's just a time interval. This also is longer and when the HTra is larger. So in very simple terms, a higher HTra value indicates more effort and is therefore generally considered more difficult to translate. This is about the product. Now, all these measures were simply about how we count the translation alternatives and how that value can statistically relate to various aspects of the behavioral data. When we use it to describe the mental processes, in addition to the use of it as a measure of the product. Now, the studies that I've mentioned here all considers word translation entropy as a product feature, a feature of the text itself, rather than the specific aspects of the mental process or the mental state during the translation process. In other words, the transition between one mental state and another. And by the way, these states are also important concepts in the active inference and free energy framework. An exception, however, is the systems theory perspective in 2019, published in 2019, which considers the process of translation as a hierarchy of interacting word and phrase translation systems, which organize and integrate as dissipative structures. From that perspective, entropy refers to the internal disorder of the system. You can see that the entropy is defined in a different manner, right, from the perspective of systems theory. This entropy would be gradually reduced, which means that the disorder is reduced and that the systems become more orderly, and that incurs effort. That cognitive effort is simply the average energy of this system. Similarly, another one looks at the entropy in the mental process from a slightly different perspective, focusing more on the probabilistic nature of the concept itself. Mathematically, there is something called relative entropy, and it's also named in other contexts as Kullback-Leibler divergence, or in simpler terms, KL divergence. We'll see this term as a recurring concept in both my later part of the talk and when we talk about the free energy principle and active inference framework, because that's an important component in calculating the highest likely action to take. Very briefly, this divergence is a comparison of two probability distributions. So it describes the difference between two probability distributions. In this discussion, it will also look at the dynamic change of probability distribution as the mental process proceeds. Rather than looking at the distribution itself, it looks at the dynamic change. Mathematically, that represents the uncertainty of choice. So by looking at the dynamic change, it also sheds light on the gradual reduction of uncertainty level in the mind. It analyzes the cognitive resource allocation in the activation, suppression, competition, and selection of candidates when multiple options are available, and also the specific processes in which the entropy in the mind is reduced through the transition of mental states. Again, when we talk about entropy reduction in the mind, this is also consistent with the free energy principle, which basically says that any sentient creature interacts with the environment through action and perception. This action-perception loop aims at entropy reduction. So all these active inference processes aim at a minimal level of entropy in the internal state. So that paper itself also analyzes the behavioral manifestations of these conceptual analyses. If you're interested, I would suggest that you have a read in the details there. So, entropy in translation. This is the first thing that I'm going to talk about. I will review some of the theoretical assumptions and discuss the conceptual basis on which entropy can describe the mental process or the cognitive activities and represent cognitive load in translation. This will naturally lead to my second part of the talk, which I have formulated two ways of quantifying this cognitive load from the entropy perspective. Entropy, the concept of entropy here is largely relevant to its definition in information theory, which is a pretty old theory proposed by Shannon in 1948. This is the equation for entropy, which is simply the weighted sum of surprisal. So if we have the probability of the outcome of an event, we can convert it to a logarithm and then multiply it by its probability. And if we do the same for every outcome of the event and sum it up, it gives us the entropy. And the definition itself is actually pretty simple. When we use it in different contexts and interpret it in different ways, it can represent different aspects of either the text or the mind. Mathematically, it represents uncertainty, surprisal, and freedom of choice. Now, uncertainty and surprisal are also recurring concepts in the active inference framework. Also, some other neuroscientific theories would propose that it is the surprising input or the unexpected input into the mental model that will be informative. And the kind of input that can be predicted or consistent with our prediction from the mental model will not be as informative as the surprising kind of input. And the unsurprising input would be likely suppressed or at least not fully processed in the mind. So yeah, I'm simply trying to say that this is related to what we will talk about in coming sessions, and that it comes back to the mathematical definition of entropy and how it represents information as formulated some decades ago. So in terms of information theory, if we consider a source of message that generates a discrete stochastic variable x, meaning x being taking discrete values from x1 to xn, and they correspond to probabilities from p1 to pn respectively, then the entropy of the information, which is the negative logarithm of each individual probability, indicates the information of each outcome, and the entropy would denote the information for the entire message. This entropy value would be maximum if all these probabilities are equal, meaning there is a high level of uncertainty in making a choice. If, however, these probabilities are concentrated on very few items, then the choice from these possible outcomes would be very straightforward, and that means a low level of uncertainty there. So that's the basic idea. From that information theoretic perspective, this is the expectation of the minimum amount of bits required for encoding. Shannon's formulation of entropy is consistent with what McKay calls the selectional information content, where the point of focus is the relative improbability of a message given an ensemble of messages. So we're mainly interested in how improbable this message is, or how surprising this message is. In addition to this, the term information also measures the uncertainty involved in estimating the value of x. That is its freedom of choice when one chooses a message. We can adopt a similar perspective for the translation process. If translation can be considered a process or a chain of decision-making activities, then the relative improbability of a certain translation option for a particular ST item, given an ensemble of translation options, can be formulated in a similar manner, right? So from this perspective, a high information entropy indicates much uncertainty, representing in the translation process a set of co-activated translation possibilities that are equally good choices for the translation of a source text item. And simply because it captures the weight of each of these alternatives rather than simply counting how many there are, it has been considered a better measure of the cognitive environment of the translators working on a given text. This is the argument given by Bangalore et al. What I will show is slightly different, but consistent to that perspective. So, in summary, word translation entropy describes the degree of uncertainty regarding which lexical TT items are chosen, given the sample of alternative translations for an ST word. Now, this is the formula that I've given previously. If all these probabilities for all the translations are distributed equally over a large number of possible translations, then the entropy will be high, and that indicates a high level of uncertainty. If, however, these translations, say, if we have a source text word that have multiple translations from A, B, until A, B, C, and D, and if all these translations are, if the probabilities for these are concentrated on one or very few items, then the entropy value would be very low, and that means a low level of uncertainty in making that choice. So that's the basic idea. In terms of indication of cognitive load, we can perhaps refer to some of the classic psycholinguistic studies that make use of surprisal and relative entropy, especially with regards to disambiguation, or particularly structural disambiguation. So surprisal is something that I'm going to explain in the next slide. Surprisal can perhaps be approximated in the CRITT database as ITra. It is mathematically, the surprisal concept is simply defined as the negative logarithm of a probability. So in the equation that I have shown previously here, if we have the probability of a particular value for x, the logarithm of it with a negative symbol would be the surprisal here. So the definition is actually very simple. But psycholinguistically, it has been considered a very important quantification of cognitive load, especially with respect to structural disambiguation, because from that perspective, sentence comprehension can be considered a step-by-step disconfirmation of all possible phrase structural analysis. And cognitive load refers to the combined difficulty of disconfirming all these disconfirmable structures at a given word. In expectation-based models of sentence comprehension, processing difficulty or measurable disruption from the behavior can arise from a sufficiently unexpected input. Again, we see unexpected input here, which is consistent with the active inference framework. And this unexpected input causes a shift in resource allocation to various alternatives in the face of uncertainty. As Levy argues in his work, in this work, the size of this shift is indicative of the cognitive effort in this process, and therefore can be used as a quantification of that effort. The size of this shift can be calculated from the change of this probability distribution over possible interpretations before and after the current word in question. Mathematically, this change of probability distribution is represented by relative entropy, or the KL divergence. I have already explained that the KL divergence describes the difference between two probability distributions. So if we have one distribution before processing the word and another distribution after processing the word, then we can get the divergence there. Perhaps from the active inference framework, we would describe that as the prior and posterior probabilities, or the PX and the QX, which will be touched upon in coming sessions. To Levy, this shift and this relative entropy is the re-ranking cost in incremental disambiguation. And these studies are from psycholinguistics, and they have to do with structural disambiguation. The basic conclusion there is that surprisal and relative entropy can represent the cognitive load involved there. In the process of translation, as I've just explained, we hypothesized that all the possible translations would be subliminally co-activated upon encounter of a particular source text item. And this assumption has been consistent with empirical studies in both bilingualism and translation process research. So we build on that to analyze entropy in the mental state. As I said, a higher entropy indicates higher uncertainty. This can be a result of either a larger number of alternatives that are activated or a lack of highly likely choices among these activated items. This activation in many models of the mental lexicon would be directly affected by surrounding linguistic context or context. This is consistent with the BIA plus model, which is this is simply a model of the bilingual mental lexicon. And there is another model which is called the reordered access model, which argues that the relative frequency of alternative meanings determines the order in which they are activated and compete for selection. But this order can be changed by a bias in context. So these alternatives are not activated at the same time, but there is a relative speed by which these are activated. In some other models, there is a combination of enhancement and suppression in the mental processes. So they can, after this activation or at the point of activation, the contextually relevant information would be enhanced and the contextually irrelevant information would be suppressed in the mental processing. So these are the general assumptions when we use the same perspective for translation. Specifically, the effect of what I've just described means that there would be probabilities observed in the text among these translation choices. Or in other words, there would be a distribution of probabilities for these translation choices. That's what we can observe from the text. And that means not all these options are equally probable. In other words, they're not equally appropriate for this particular context, given the source text. And that probability distribution, as I showed in the mathematical equations, can be described by the entropy value. As a feature of the product, this entropy value would indicate the level of uncertainty in the selection among the possible TT items in the sample. Now, this is about the products. When we use the same perspective for the translation process, we can assume that the translator involves in an activation pattern of the possible translations, where each of these activated items would receive a different degree of priority for resource allocation. Or if we adopt a reordered access model, they would be activated in a certain order in terms of relative time course. This activation would be affected by linguistic context, and they can appear in the text as a distribution of probabilities we can observe in the product. In other words, the probability distribution in a product can be considered a manifestation of this activation pattern in the mind. In the subsequent mental processing, this activation will be dynamically updated to arrive at a translation choice. So when all these items are activated, and as these items come into competition for selection, the translator would likely evaluate these options and consider some contextual factors and receive additional information input so that some options would become more likely than others and some other options would become less likely. And that means this pattern would be updated and the probabilities associated with that pattern would be updated accordingly. So if we have this process, then each mental state would correspond to a different activation pattern and a different entropy value that describe that pattern. Eventually, that entropy level would be reduced to a reasonably low level. So at any 2 points in this process, we can compare the entropy level in one mental state and the entropy level for another entropy state, and that, essentially those are probability distributions. So entropy, therefore, can describe this pattern in the mental state, and it describes the distribution of resource allocation or the distribution of temporary probabilities with which a particular item would be selected at the end of this mental process. Yeah.
Sorry to interrupt you. May I ask you a question?
Yes.
At the top of this slide, you talk about the probability observed in the text. How do you get a distribution? Because you have a translation, you have presumably one translation per item.
So if we have a source text, say, if we look at this sentence itself, right, as the source text in our experiment, we would have a translation for each word in the produced translation from the participants, right? And say if we're looking at probabilities, if this word corresponds to several translations, say in Chinese, then these, say, translation word A, B, C, and D are the possible translations for this word. And from the experiments, we can get a frequency of occurrence for each translation. These frequencies can be converted to probabilities and then to entropy, right? So for each word in the source text, we would have an entropy value. And for each word, we would have a probability distribution of all the possible translations for this word in the target language in question. Does that answer your question?
Yes, so I guess it really relates to the number of participants you have in a particular study to get a resolution on that distribution.
Right, exactly. From the in the CRITT database, that was approximated from the experimental participants, right? The choices that the participants have made. Ideally, I think if we talk about the mind, we would ideally have all the possible options for this word and the distribution of probabilities either from a corpus or a well-balanced corpus, or if we somehow miraculously have access to someone's mental lexicon, we would want that probability distribution in the bilingual mental lexicon. Yeah, but in practice, this entropy is operationalized and as an approximation from the experimental session. So in the CRITT database, the HTra value more closely relates to the choices that all these participants make rather than all the available choices out there in the language itself. Yeah.
Thank you.
Yeah. Thank you. So, so that's about entropy in the translation process, which concludes my first part of the lecture. And the second part of my talk has to do with quantification of cognitive load. We have reviewed the assumption of co-activation of both the source and the target, and I've described that the translator involves in an activation pattern where the activated items receive either different degrees of priority for resource allocation or the or speed by which it is activated in terms of relative time course. And this activation will be dynamically updated. I'm talking about the mental states rather than the entropy in the text. So in the mind, this activation will be dynamically updated, which comes with a continual shift of cognitive resource allocation, which incurs cognitive effort. And that change of distribution of probabilities also results in a change of entropy, or specifically a reduction of entropy. Now, again, I'm talking about the mental state, and I'm talking about a particular point in the text, right, with respect to a particular word in the source text. So from this perspective, we would naturally have two ways of quantifying it. One is the shift of resource allocation, as I've just described in the psycholinguistic studies, as formulated by Levy, which would be calculated from the relative entropy. Right? And another way we can quantify this process is by looking at how much entropy is reduced, right? The extent to which entropy is reduced. So entropy reduction can also be another metric. If we have two mental states, we can either calculate the relative entropy of these two states, which represents the shift of resource allocation, or the absolute difference of entropy value of these two. Those are the two that I'm going to compare. So the shift of resource allocation as formulated by Levy, or the processing in the psycholinguistic studies, is relative entropy, and I am going to do some mathematics, and I'm going to argue that this relative entropy is equal to the surprisal of the item that is eventually selected at the theoretical level, and this surprisal can perhaps be approximated from the empirical data via word translation information, or ITra, in the CRITT database. So the choices by these participants can be arguably considered an approximation of what's being analyzed here at the theoretical level. The other perspective, which is the reduction of entropy, I will argue is the absolute difference of entropy values between two mental states, and can be approximated by word translation entropy as denoted by HTra in the ST tables. So if we have the initial activation pattern, which corresponds to a distribution of px, and then the final selection stage after all these competition among the alternative candidates, the eventual distribution denoted by qx, if we have these two, and if we assume that there are n items in the mental lexicon, among which, all these n items are activated, of course, and among all these n items, it is word w that is eventually selected. We can make use of these symbols and do some mathematics, and perhaps provide some proof of this relative entropy being equal to the surprisal of the item of w, and that the reduction of entropy is equal to the initial entropy of px. So that's what I'm going to do. Relative entropy is the same as the KL divergence, the Kullback-Leibler divergence between these two distributions, Q with respect to P. And by the way, when we talk about the active inference, we will also use KL divergence, and P would be the prior probability and Q would be the posterior probability. So the divergence between these two, by definition, is calculated in this way. And if we take out word W and all the rest and do further mathematics, eventually we come down to three parts. The further mathematics will show that this part equals 0 and that part equals 0. So the KL divergence will be equal simply to the negative logarithm of PW over here. This means the relative entropy between these two is equal to the surprisal of W. So that's what I'm trying to say here. The relative entropy is equal to the surprisal of the item selected. Now, if we use that perspective to represent the cognitive load, then the surprisal of the eventual choice would be an indication of this load, or an approximation via ITra would represent this cognitive load. So from a different perspective, if we have the decrease of entropy, or the absolute difference of entropy levels between two mental states, we can get the initial entropy at the activation stage and the eventual entropy H1. And some mathematics will show that the H1 perhaps is 0, and H1 minus H0 minus H1 is simply H0, which is exactly the same as the equation for word translation entropy. And in the CRITT database, it is approximated by HTra. This means that the decrease of entropy would be approximated by the HTra value. In short, the shift of resource allocation represented by relative entropy is shown to be equal to the surprisal of the item that is chosen at the end, and that can be approximated in the data by ITra. From another perspective, the reduction of entropy is the absolute difference of entropy values between these two mental states, and that's the entropy generalizing over all alternative options, which means that's the HTra value that can be operationalized. Yes.
Can you say in what sense, what does it mean, shift of resource allocation? In what sense is this shifted? What is shifted there?
So we might either look at, I think this has to do with the serial versus parallel processing, right? If we assume that all these items are processed at the same time, then there would be a distribution of the resource, right? These resources would be allocated to all of them. But if we adopt a serial processing perspective, then at each point of time, only one option is considered and attended to, and that might indicate the how likely it is for the processor to attend to a particular item, right? That's my understanding. What I mean by that.
Would that mean that a translator might first think of translating something as cup, and then they think, oh no, maybe mug, maybe what else is there? So they would go through these different kinds of options that is there, and that is a relocation of resources.
Yeah, if we adopt a serial processing perspective, yes.
Okay, but this implies serial processing option that you propagate there by calling this shift of resource allocation.
Right, but in the meantime, I think it's also consistent with a parallel perspective, because if all these options are allocated some resources, then what I mean by the shift is that the distribution is changed. So, yeah, that's what I mean by it. Yeah, thank you, Michael. So theoretically, we have these two, and both can be approximated from the text or from the experimental session. We may have different ways of operationalizing it or approximating the level of entropy here, but in the CRITT database, there is one way, which is from the experimental session. Okay. So we have two ways of operationalizing it, two metrics. One is HTra and the other is ITra. As a measure of the product, HTra generalizes over all translations, all possible translations, or in the CRITT database, all the choices that the participants have made, whereas ITra indicates the unpredictability of a specific item. So ITra has to do with one particular choice, whereas HTra has to do with all choices. That's a description of the product. As a description of the process, HTra is the reduction of entropy, as I have shown, in the transition of mental states, and ITra is the size of shift in this cognitive resource allocation. So that describes the mental states of the initial activation stage and that of the final selection stage. In terms of the mathematical equations, HTra would represent the initial px distribution, whereas ITra is simply the surprisal of the final choice. And HTra is the absolute difference of the entropy between two mental states, whereas ITra is the relative entropy of the final state with respect to the initial. So we have these two. And a very interesting question that will follow is which one is a better predictor, right? We have empirical studies that show that HTra is a predictive feature for effort, and ITra is also a predictive feature of effort, but which one is better? And theoretically, they reflect different perspectives. And that is what I'm going to do in the final part of my talk, which is entirely empirical. Prediction of effort. We use the CRITT TPR-DB. There is a data set called multilink, which includes a set of source texts in English and translate it into different languages in different translation tasks. So all these experiments come from the same source text, and that provides a very convenient ground for making some comparison and doing some systematic analyses. I've used 500 sessions in 6 studies and looked at the measure of effort, both in terms of time of production and in terms of the reading or the metrics as we can get from the eye movement data. Production time in the data set in the ST table is denoted by DUR, which is basically the duration of the TT production for a particular ST token. Reading time has different measures. We have early measures, including first fixation duration, first pass duration, and so forth. Right? First fixation duration is the time interval between the first fixation on this word and the first time the eyes leave this word. That indicates some of the early processes in the cognitive mechanism. And we also have the total reading time on both the source and the target, which means the totals, the sum of all the fixations on this word from the eye movement data. And that will include some of the late processes in addition to these early processes. So I've looked at these in relation to HTra and ITra respectively, and did some multiple regression analyses. VIF score here is an indication of the collinearity between the variables, and they seem to be within an acceptable range. So what I'm going to do is just to show the results of some regression analysis for these dependent variables in relation to HTra and ITra. There's a question from the chat. Could you please simplify the terms that are of relevance to entropy and how to operationalize entropy? So in very simple terms, entropy indicates the uncertainty in the choice, or the probability distribution of that choice. If we have, say, a source text word that has 4 translation options, and all these 4 options are very much equally likely, then we would have a very high entropy value. If, however, only one of these options would be the most frequent one, or most commonly, we would only use option 1 as a translation, although there are other choices, then the probability distribution would be concentrated on option 1, right? And that means the entropy will be very, very low. So that's entropy in very simple terms. And to operationalize entropy, we do an experiment and follow the procedures of the CRITT methodology, generate the tables, and one of the tables is called the ST table. In that table, we directly have that column called HTra. So in practical terms, right, that's what we do. But what the CRITT database does in calculating this entropy is to get all these translation options from all the participants in that experimental session, and then use the formula that I've shown to get the value. So prediction of effort. Now, this is the regression analysis. Results are pretty interesting. As I've mentioned, I will be using the R-square and the coefficients in the regression analysis that we have learned last Friday. So if we look at the Python script last Friday, we see a lot of numbers in this regression results, which can be somewhat confusing and mind-boggling if you're new to this. But what's really important, and I've already mentioned at the beginning, is the R-squared, which indicates how well the model explains the data, the coefficient here, which shows the relationship between these 2 variables, and the p-value indicating statistical significance. So if we have base models with HTra in relation to production time being the dependent variable and HTra being the independent variable, we see that the model explains 3% of the variance in production time. and the p-value is small, indicating that it's statistically significant. The same for ITra, but ITra explained 2% more of the variance in the duration. These are the base models, but we can also put both into the regression analysis, and we see an R-square of 0.05, and the p-value is also very small. These are the base models. This is the full model. This base model in Dura1 has HTra as an independent variable and duration as dependent variable. This part has ITra as independent variable and duration as dependent variable. So that means ITra seems to explain a more percentage of the variance in the dependent variable. And what we can see in the full model is that the coefficients show a big difference between these two. Now, this analysis is with the standardized beta values. Beta values are simply the coefficients. So these beta values are standardized, and that means we can compare these two. We can see that the coefficient for ITra is much larger than HTra, meaning ITra is more than 3 times as a stronger predictor than HTra, right? And we can also see from this result that with ITra controlled, no additional variance was explained by HTra, simply because adding HTra doesn't really increase the R-square. In contrast, after controlling HTra, ITra explained an additional 2% of the variance. So from here, with HTra as an independent variable, if we add ITra to the same model, then we have a larger R-square there, meaning ITra explained an additional percentage of the variance. So, while controlling the other variable, ITra made an additional contribution in explaining the variable in production time, whereas HTra did not. All these seem to suggest that while these two are both statistically significant in increasing production time, ITra seems to be a better predictor for production time than HTra. When we look at the fixation data, we see something quite different. We see something quite the opposite. So for reading time on the ST involving all these early and late measures, all impacts in all models were significant for all measures of ST reading time, which is consistent with the previous slide. But what's sharply different is that for both early and late measures, HTra seemed to be a much stronger predictor than ITra. This is the opposite than the previous results. So for all these, HTra is more than 3 times or 4 times as strong as ITra. Now, if you're interested, you can just do some analysis yourself and then look at the details from the table. This is included in the references that I've just mentioned at the beginning. For TT reading time, we don't really see a large difference between these two, although all predictions are also still significant. So that's just an example that I want to show of using regression analysis for this kind of research topic. And that compares these two metrics in predicting cognitive effort. What I'm going to show is later on is still empirical, but with a slightly more of a qualitative perspective, and look at the specific processes of eye movement and how the theoretical discussion on the mental states can be manifested by observable behavior. Eye movement. I'm going to use one example, which is a phrasal verb used as in a metaphorical sense. It is cough up here, which is very different from the normal sense of coughing. So the source text is about the increase in cost of living, and the source text goes, British families have to cough up an extra £31,000 a year. So the cough up is used metaphorically, which presumably would be somewhat surprising than the normal sense of coughing, and it will correspond to a different translation than the literal meaning of coughing. What we see is that in the process of producing the translation, the translator would come to a pause at this point of cough up. And the eye movement shows some very interesting pattern here. The path here is the eye movement path. So the translator stops at the point of cough, and then the eyes move from to cough, and then stay there for a while, and then the eyes move back to families, and then back to in, and then to increase. All these words in the code text are somewhat related to coughing up, and they facilitate the resolution of the translation problem here, or contextualize a translation choice for this phrasal verb. What is interesting from the entropy perspective is that the word that causes this disruption of processing has a very high entropy value here. That's the HTra for cough. And all the other words that are fixated to resolve this problem rising from the high entropy item has much lower entropy values. And altogether, this entropy value is dragged down to a much lower level than that for the cough itself. So this shows that high entropy the high entropy item results in some disruption of processing and some difficulty in problem solving, and the process of this problem solving involves information from the lower entropy items in the code text. We can also analyze it from the progression graph, right? So this is another example of it. We see that this part is a pause of translation production before the translator proceeds to translate have to cough up. Right? In this pause, the eyes would scrutinize the source text, showing very obvious regression of eye movement, and then rereading linearly, and then another rereading at an earlier part of the sentence, and then moves back to the original point, and then starting the production again. So this indicates disruption of processing or extra processing effort. And if we look at the entropy levels of all these words fixated, we also see a similar pattern as here. So two examples of it and two ways of looking at it. In the CRITT data set, again, from a discussion on 200 participants for multiple languages, we see a pattern for this phrasal verb. There seems to be a pause in production and regression of eye movements when it comes to this phrasal verb, where the scrutinizing of the source text tends to involve a visual search for low HTra words in the code text to facilitate that problem-solving process. And this is a decrease in the average entropy of the activity unit. We could probably say that all the theoretical discussion on entropy can be manifested in behavioral data as a decrease of average entropy in the activity unit, as well as a visual search for information carried by low HTra words in the code text. So, activity HTra in activity units. To resolve the problem from a high entropy item, the translator needs additional information for clarification or disambiguation, and therefore it is not surprising that we observe gaze on other words in the code text. Right? It seems that the high entropy item effectively directs the translator to those aspects of the context which are relevant to integrating the newly activated information into what has already been activated, to enhancing or suppressing certain activations depending on the appropriateness for the context, and also reducing the uncertainty level in the mind to eventually arrive at a selection. As all these words correspond to lower entropy levels, we may also interpret that in relation to horizontal translation process. If we look at the nature of this phrasal verb, the problem seems to be its metaphorical use, right? There's a description of its origin by Side, which says that cough up is highly idiomatic And as a child, if I choked on my food, my father would thump on me on the back and cheerfully cry, "Cough it up. It may be $50." This is what he describes as the origin of the phrasal verb. And some studies in cognitive linguistics would argue that without a frame described by, for example, a site, it is almost impossible to understand the idiomatic meaning of cough up. And I think the important question is here, if we observe a low entropy associated with the visual search, does the translator aim to understand the metaphorical sense at a conceptual level, or invoke the frame as proposed by Side in order to translate? Or does the translator stay at the linguistic level purely and involve in a direct and memory-based search in the mental lexicon without much of the conceptual mediation? And that has to do with horizontal versus vertical processes. There have been two perspectives. The vertical process of translation would argue that this is conceptually mediated. So the process is that the ST message is first decoded, and then there is a conceptual representation activated, which would then be transferred to a lexical representation in the target language. So it goes to the conceptual level, whereas horizontal translation would be more in the lines of transcoding, which is a direct online and memory-based searches for links between the linguistic entries in the two languages. There would be no conceptual mediation involved, and there are some experimental studies showing that there is some horizontal processes in existence, even if the vertical process is there. So it seems that both are in existence, and that the horizontality is gaining some more evidence in recent studies. They also have to do with a sequential versus parallel processing perspective. The vertical translation process argues that the ST reading stage is distinct from the reformulation phase. So ST reading and TT production are different processes, whereas horizontal perspective would suggest that the reformulation processes would already occur when the ST was read. So both the ST comprehension and the TT reformulation occur at the same time. And that basically is a parallel processing perspective. Another study that I've included, and that's included in the references published in 2016, uses entropy or word translation entropy as evidence of this horizontality of translation. So here, back to the point, if we have this observation, and if these items in the surrounding code text correspond to low entropy items, and by definition, this entropy represents TL, or target language related processes. They capture aspects of the TL activation during ST reading. Perhaps this observation of the visual search in this example, the low entropy items in the context may represent the readily available TT code text, which is activated in the translator's mind, or at least these are more easily activated or more quickly activated during the visual search. So this activated TT code text would facilitate the selection of a TT option for the translation for cough up, or the item being translated at this point of time. From that perspective, I think these observations can perhaps be interpreted as a direct memory-based search in the mental lexicon for a translation option which is linguistically compatible with a TT code text rather than a mental process which is based on inference and reasoning over representational structures, or as we say in the horizontal process, in the vertical process, over conceptual comprehension. So from that perspective, perhaps we can interpret the cognitive processing as largely horizontal, or at least there is existence of horizontality to a considerable extent. I'm not really saying that this is absolute, but it might shed light on how we look at the horizontal versus vertical processes. In conclusion, I've analyzed two ways of quantifying cognitive load, both at the theoretical level and the empirical aspects. So one is shift of resource allocation and the other is reduction of entropy. At the conceptual level, HTra is the reduction of entropy in the mental state, and ITra is the size of this shift. Hopefully I've provided some theoretical justifications for both of these two metrics as potential means of quantifying or predicting cognitive load. And in the empirical analyses, we see that both metrics are significant and strong in increasing cognitive effort, and ITra seems to be a stronger predictor for word production time, while HTra is a stronger predictor for ST reading time, which is not really surprising because ITra, by definition, is from the eventual choice, which might, when we look at the cognitive processes, might come later, whereas HTra is more related to the activation stage, which is very much early on. So we see that for ST reading after this. We see this impact for ITra for the TT production. The difference for the two, for TT reading, was found to be relatively small. And after this, I've also looked at the eye movement, the specific process and dynamics of the eye movement in resolution of the problem arising from the high entropy item. Hopefully this will give us some insights as to what we can do with the database and what theoretical aspects that these analyses can shed light on. Again, these are the references that the main references that I've touched upon. If you have any questions or after this session, or if you're interested in some further discussion, you're most welcome to send me an email and then talk about it.